Hello, my name is gunwant purbia and from group 316. My topic is the method of investigation of structure of biopolymers. In the first, the X-ray diffraction analysis. X-ray diffraction analysis. Before we delve deeper into the study of protein, let's explore the method used to investigate the structure of biopolymers. The field of the natural science employs two main methods to study the structure of atoms and the molecules, in which chemistry and optics. While chemistry reveals the primary structure of biopolymers and the structure of a functional protein centers, it cannot categorize the spatial three-dimensional structure of protein or nucleic acid. The X-ray diffraction, on the other hand, provides direct information on how atoms are arranged in molecular and crystal. X-rays are the electromagnetic waves which are scattered by electron shells of atoms. When X-rays is scattered by a crystal, the diffraction can be seen at the reflection of X-rays from the crystal lattice planes. This phenomenon occurs when the scattered waves are in phase, meaning the difference in the distance travelled by the rays is equal to an integral multiple of wavelength. Diffraction patterns are determined by the intraatomic distance in the lattice, which is comparable to the wavelength. X-ray diffraction helps determine the spacing between the atoms based on the diffraction pattern obtained for known wavelength. To obtain detailed information on the substance structure, crystal needs to be investigated where atoms are arranged in a regular periodic manner. The crystal lattice is characterized by the three periodic rather than one, and there is a set of crystal planes that reflect X-rays. These planes are identified using Miller's index, and each plane has a different interplanar spacing. X-ray diffraction patterns show a series of diffraction maxima resulting from the reflection of nanochromatic radiation by crystals, which allows for a deeper understanding of the substance structure. The electron density distribution in a crystal is derived from the diffraction pattern and is expressed as the structure amplitudes, which depends on the number of electrons in an atom and the scattering direction. Structure amplitudes are complex quantities characterized by the molality and phases. These phase of the reflection is essential for establishing the material structure. This is the X-ray diffraction, as you can see. To determine the phases, heavy atoms like mercury are added to protein molecules within a crystal as part of the heavy atom method. The difference in diffraction spot intensity with and without heavy atoms helps to determine the phase. This method allows for unambiguous phase determination using the protein derivations containing heavy atoms. The electron density distribution is depicted through electron density maps connecting points with the equal density values. The ultimate goal of X-ray diffraction analysis is to create three-dimensional model of the protein molecule showing the position of all atoms. This approach has been vital in unraveling the structure of complex molecules like protein and the biopolymers. The study of biopolymers, particularly proteins, using X-ray diffraction has been a significant breakthrough in molecular biophysics. Notable achievement in the area can be attributed to the researchers from the Cambridge Research School, such as Bragg, Fendrew, and Patrick. These spatial structures of proteins like myoglobin has been elucidated using X-ray diffraction techniques, shedding lights on their intricate atomic arrangements. Protein crystals necessary for X-ray diffraction analysis are challenging to cultivate as they are complex molecules. Lattice with the large water content. Denaturation of this molecule can occur before the crystal melts, making their study complex. The interpretation of X-ray diffraction pattern is a multicellular protein requiring electronic computer assistance due to the vast number of the reflections involved. High resolution X-ray diffraction has been achieved for numerous globular proteins, offering detailed insights into their structure. Enzyme protein complexes and the inhibitors have been also been studied using X-ray diffraction methods to understand their interaction and the function at the molecular level. The fundamental question of whether the structure of a protein in a crystal corresponds to its biological functional form in solution and has been a subject of investigation. The study has been shown that the structure data obtained from X-ray diffraction are generally consistent with the optical measurement of the protein in solution, indicating the crystalline protein retain their biological activity. Furthermore, the interpretation of X-ray diffraction patterns of the fibrous biopolymers like collagen and the DNA has revealed specific features unique to their periodic one-dimensional structure. The analysis of these patterns has led to a better understanding of the helical structure observing in biopolymers. Overall, X-ray diffraction analysis continues to a powerful tool in elucidating the structures of complex molecules like proteins and the biopolymers, offering valuable insights into their functions and interaction at the atomic level. Now the second topic is diffuse scattering of X-ray by the solution of biopolymers. It provides information on the distribution of scattering objects. This type of scattering is the total scattering by randomly arranged individual macromolecules, where the scattered light intensities are arranged over all position orientation of the macromolecule. Small angles scattering is used to study the gross structure of macromolecule in solution, while the medium and large scattering angles are used to probe specific internal structure feature. The theory of small angle diffraction is based on concept similar to light scattering theories and allows the relationship between scattering intensity and distance between scattering particle to its star. To determine the shape of the macromolecule, assumptions such as the spherical, ellipsoid or the extended cylindrical shape are made. Scattering indicates have been utilized to determine the size, shape and the molecule weight of various biopolymers, and the large angle scattered provides detailed information on the shape of the homogeneous particle, categorizing structural details with the dimensions ranging from 4 to 0.1 nanometer. The X-ray scattering calculation considered the effect of solvent on the intrinsic shape. Native proteins exhibits domain structure mobility as evidenced by the X-ray diffraction analysis. Comparison between the experimental and theoretical indicates suggests limited mobility in the structure of the ribonuclease lysozyme and their inhibitors, both in the crystals and in solution. However, the slight difference in the intrinsics suggests fluctuation in the protein domain scapes. Significant differences have been observed in the structural data of crystalline and dissolved proteins, indicating structural variations in protein in the solution due to the domain displacements. In conclusion, X-ray scattering by the biopolymer solution offer valuable insights into the distribution, structure and mobility of macromolecules. The data obtained from the skating experiment contribute to the understanding of the shape and the internal organization of these biological molecules, shedding lights on their structural characterization in different states. These findings underscore the dynamic nature of protein in solution and highlights the importance of the considering environmental factors such as solvent in structural studies involving biopolymers. Thank you.